How was Leatherman?
Good.
You like it? Yeah, worth doing?
Yes.
Okay. Where do we go this Thursday? Yeah, Lightbox right down the road. Have it as an 8-minute drive. They're strongly encouraging us to carpool because they have limited parking. So there is a gate, and no matter how many times they'll tell me what that process is, it changes based on the security guard at the gate. So when you pull in, just identify yourself as Mount Hood students and they should let you in. But that's all you can do. But there is a gate, huh? We haven't had to have anything like that in the past. But sometimes there's like a dysfunction between the inside people and the outside people. Like you might not know, or she might not know there's a tour, so we might have to make a phone call. So it's probably the first people there that will have the most trouble. The rest of us will just sail right in, but it's a pretty secure site. We have a lot of investment in diamonds there, so they have a lot of floating around diamonds. So it's pretty fun. Kind of the same protocol on dress, no open-toed shoes, no loose clothing. They in the lobby area, they'll have us there for a while, and they've let us take pictures there in the past of the diamonds, and often we get to handle the diamonds, which is pretty cool. It's like, you know, millions of dollars in your hand type of thing. It's kind of fun. I'm sure. Good luck, man. I don't know. I wouldn't go for it. Tour starts at 2. We need to be there by 1:45. Walking in the door kind of thing, jamming up their lobby.
Is there gonna be an iPad situation?
I don't know. It wasn't last time, but there was just pencil paper waivers that you signed. So, yeah. Also, there was a guest speaker last Tuesday, and I don't think I told you about it in class, and a lot of people missed it. Jamie Kilgore. So if you want to do it, you can get the points, you can still do it. Do it. Okay. There is a guest speaker this week also. I think I put him here on Thursday, I think. Yeah, Josh. So there's one on Thursday. Don't forget to do that one. Also, I put up the document for the final packet. So we're going to do the challenge in 2 weeks from Thursday, right? After the challenge, you then have another week to develop this final packet. And it really should be just pulling things together and making it organized and neat. Maybe a little narrative to explain it. But you should look over this, and if you have questions or don't understand one of the bullet points, ask me. That comes in on there, the 19th. That's essentially your final. You can deliver it in person or you can upload it. Up to you.
Wait, so during finals week, we have to show up for in-person?
You do not. You just got to get that thing delivered. Yep. Final challenge is here on the 14th. We don't have much time left. This is close. This is like the second to the last day for that. You can come in and sit down if you want, Kevin. Or you can just stand. I'm good with just standing. I'm a stand-up guy. Kind of. All right, questions on anything about that kind of stuff?
Either go or.
Yeah, I think it's a 2 to 3 1-hour thing. I remember last time though, they split us up and one person was pretty chatty and took longer than the hour. So if you need to be out of there by 3, do you need to be out of there by 3?
No, I'm just asking.
I think they're gonna want to keep the group together.
I'm just asking, like.
Yeah,
I don't know
yeah.
anything yet, but I always.
Just identify it if you can to me, and then I'll try to accommodate that for sure. Yeah. All right. Today, before I go into additive manufacturing, I'll talk about that a little bit. I just want to bring 2 sites to you for the professional engineering license and the fundamentals of engineering license and the engineering technology certification exam. So there's those 3 possible things. The thing that would be on the radar for the transferring students would be the fundamentals of engineering exam between your third and fourth years when you should take that. And then if it's not, if you don't pass it, then you take it again at the end of your fourth year. Okay, so this site is up on Blackboard. It's the NCEES site. And they organize and administer these exams. So if you go into here, you can see FE exam, PE exam, and then there's different ones for surveying. There is another site for the certification of engineering technologists. I don't often have two-year students take this, but I love it when they do because it's a certification, right? It is. Then you have an AS degree, an associate's degree in engineering technology, and then you have a certification from an exam. Same as the transfer students, you're going to get a bachelor's degree in engineering. That only means so much. If you pass the fundamentals of engineering exam, that means a little more, right? And then in 4 years after you graduate, if you chose to take the PE, you would have that route. Okay. Yeah.
For these tests, is it kind of like, the type that you kind of have to pay to get in?
Oh, you definitely got to pay to get in. Yeah. It's not, it's like $200 to take the test.
Okay,
So it's not I mean, compared to your education, it's cheap.
yeah, because
Compared to that.
my brother, he studied to be like a physical therapist. He
Mhm.
had to take a test and
Mhm.
kept failing over and over again. That was $500.
Yeah, most professional organizations have to do it, right? Nurses have to take the nursing exam to become an RN. Doctors have to take, lawyers have to take, engineers have to take. Yep, yeah. Yep.
You say after 2 years?
Definitely after the 2 years. And actually, I think they want you to work a little. So I'll put this site up. I haven't put the link to it yet, but I was reading about it this morning a little bit. I think including work history. So I think you have to go to work for a while as an engineering technologist before you can sit for it. And then it's an application process for the 2-year folks. I don't know if anyone hasn't been approved to take it, but you got to apply, you got to give them your portfolio and your information from your institution, that kind of thing. This is actually interesting, I think. It is there are organizations that are very pro the engineering exams, like they really want you to take those exams. I think you absolutely should take the FE because that is going to be a killer. Even 1 year after school, that'll be a killer to take it. You'll have to like re-study up. When you are in school, all this knowledge is floating around your head. You don't think you have it, but you actually have quite a bit, right? And then every year that you're out of school, it's gone. Let me tell you. Just ask an engineer somewhere, to help you with your homework, and they're gonna be like, nope, can't do that. That was a long time ago, right? Unless it's the area that they're working in. Like, if they're working in strength of materials and they're doing design of specialized materials, then they can probably do a strengths homework problem, no problem, right? But give them a fluid mechanics problem and they'll be like, no, I don't do that stuff, right? So as time goes on, this, as time goes on, we lose that knowledge. School is like the perfect example of that. Like my strength students had statics last term and it's already gone. Like what? We just spent 10 weeks doing this. So it is definitely something you want to do right away. All right. So those 2 sites will be up. Let's just look at the FE exam. See how they're doing it now. It's a computer-based exam, administered around. Let's just look at this. You can see that, right? Oh, good. So I'm sure it's much different. Round and single day exams. Yeah, I guess a lot of, here we can look at it.
Examinees taking a computer-based NCEES exam may see up to 5 types of questions on their exam. The question types include traditional multiple choice questions that feature 4 4 answer options from which to choose, one of which is the correct answer. Multiple choice questions with multiple correct options.
Which of the following are stormwater erosion classifications? Goalie. I'm just curious how. The toughest questions are the ones that say choose the most correct answer. That means there's more than one correct answer and one is more correct than the other. Like, really?
Feature more than 4 answer options from which to choose and allow for multiple answer options to be selected. Point and click questions require you to select one or more predetermined clickable
That gives me shivers. That's thermodynamics.
areas that become visible when you move your cursor over the graphic. Drag and drop questions require you to click and drag your answer options to sort, rank, match, or label a provided graphic. Fill in the blank questions require you to enter your response instead of choosing it from a list of answer options.
Engineering economics, it's a good class. All right. That's good, yeah.
How long was the test when you took it?
It was 8 hours when I took it, and I think it's 6, didn't it say 6 hours? No. Yeah, it was 4 in the morning, 4 in the afternoon when I took it. Yeah. And again, I don't know all the details, but when I took it in the morning was random. It could be on any topic. And in the afternoon, you got to choose 2 topics and that's what it was focused on. So like in the afternoon, I chose like electrical fundamentals and strength materials or something. And then all the questions in the afternoon came to me in that area. So I don't know if they do that now or not. Don't know. I know it's not as long. It's not 8 hours, but we could also take like resources in. So people literally had wheelbarrows of books they were taking in. It was crazy. People packing all kinds of stuff. And I don't think that's the case anymore. All right, let's talk about additive manufacturing. So that's what I'm gonna call it, additive manufacturing, not rapid prototyping. Rapid prototyping is one of the additive manufacturing processes. So what is a subtractive manufacturing process? Any ideas? Yeah, so when we were at Leatherman, the first process we saw in our group was a stamping process, right? Where you take a solid piece of material and you stamp out the part you want, you subtract out the part you want, right? Leaving the waste. Now they're dealing with the waste by either selling it or recycling it or something, but it's still waste that has to be managed and there's energy and effort that has to be put to it. So exactly, subtractive is primarily what we do. It is the largest portion of manufacturing that's currently going on. We take a big chunk of something and we whittle it down into smaller pieces of something, or we form it, right? We take something like this and we form it, stamp it, punch it, drill it. We subtract out the parts we don't want. Okay? Additive is the opposite of that, where we just add the material that we want. The oldest additive system out there is welding. Welding's been around for a very long time. When you weld, you're adding material, right? So you're adding just the exact material we want. And there's actually additive processes that are a lot like welding. Just think of a plate and charge that plate with electricity and then bring your electrode down. It creates an arc, which is a weld, and then it runs a path. And it literally lays a bead of weld down, and then the table drops and it does it again. That's an additive process. It's essentially just automated welding. And it's used out there. Some, not a lot, but some. All right, so let's talk about the different prototyping systems that are out there. Maybe you've seen this stuff, maybe you haven't. There's essentially this wheel for different parts of the rapid prototyping There's the input part, the method, the material, and the application. So this wheel kind of organizes how you would use rapid prototyping or additive manufacturing. You're not just gonna just go grab a machine and say, this is what we want to work with. We have to decide what material we want to work with. We have to decide what scale we want to work with. What method is the best for that? So input is gonna be your model, right? That's gonna be something like SolidWorks. So here's a SolidWorks model. We're gonna spend time drawing it up. Anybody in SolidWorks currently? One in the back? Anybody taking it in the spring? Yeah. So in the spring, you'll start with the input, right? The input is how we get this model. Most often it's something like SolidWorks where we model it, but we can do other things now. Right? We can do it from a physical object. So we can take an object like this and then take a 3D scanner and scan it. And that 3D scanner can be up to within a thousandths of the object. And a thousandths is pretty close. That's 0.001. In other words, it'll be a thousandths accuracy of this exact object. When you scan it, it'll make that three-dimensional object and you can pull it right into SolidWorks. And then you can adjust it or modify it or do design work with it. So we can do the input from a solid object, but most often it's done from a software and us actually modeling it up, right? So once it's modeled up, then we have to choose what material we want to make it out of. That will be big because that'll choose the machine. We can rapid prototype any material at this point. For so long, it was just plastic extrusion and plastic parts, but now it's anything, whatever material you want. This one is aluminum. This one is also some kind of aluminum. I have a stainless steel one in here. This is stainless steel. These are all rapid prototype. So you can look at all these here in a bit. Actually, you can look at them now if you want to pass them around. Or not. These come out of the rapid prototyper exactly as you see it. So there's no assembly, right? So this bimetal one has both copper and aluminum in it. And it is a little storage device. So it has actually some electronics in it too. And that all got rapid prototype. This I want to talk about in a second. This is a table. And this is when we run an optimization on a part. So the advantage to rapid prototyping is you don't have to make multiple part assemblies. It can be one thing, right? Where this maybe typically is 5 to 10 parts. You can rapid prototype it up as one part, right? So nobody has to assemble. The assembly process goes way down. There's a slide in here that talks about the jet engines that GE is making and their part count, how they've been able to lower the part count. Caterpillar, large company that's building very large equipment, bulldozers and scrapers and backhoes. They, by like 10 years from now, will not store one part for Caterpillar products. So right now, Caterpillar parts are stored across the company, right, at Caterpillar stores and at Caterpillar warehouses. Because if you buy a bulldozer from Caterpillar and it breaks down, you have to get that Caterpillar up right now. That thing is losing you money if it's not operating, right? So they want this turnaround that's incredible. So these parts have been stored across the US for decades. And that costs money. I mean, you got to heat the building, you got to pay people to keep track of the parts, right? You got to own the land to do it all on. They're moving 100% away from that. When your bulldozer breaks down and you need part Z, you call them up and say, I need part Z, and they'll say, we'll have it to you in a day. And they will rapid prototype it and ship it to you. So they'll just start that print right now, print it up, and it's gone. right? They might have prototyping stations across the country to make that delivery a little faster, but they're not gonna store parts anymore. They had some, when I was at the conference, they had some numbers that were crazy, like, $60 million is what it costs them to store these parts over time. And then many of the parts never get sold, right? They made them, that costs money. Then they store them, that costs money, and then nobody ever needed them, type of thing. Then they have to get rid of them, scrap it. It all costs money, right? So they're gonna save this enormous amount of money by rapid prototyping parts as needed. So that's pretty cool. All right, let's jump down to the types of rapid prototyping. There's liquid, there's solid, and there's powder. So I'm not gonna go through the slides. I mean, the slides are pretty intense. I don't know how many are on here. 175 slides. You want to go through all those? I'm not up for that, right? Let's just talk about it. So I put this together from a conference I went to because I had to then come back and present it to faculty here. So now I just use it as my talking points, but I just blast through the slides. We'll get to a lot of the slides are actually just pictures I took from the conference and I want to show them to you. So liquid based. We have a liquid based printer next door that was donated to us that we've never gotten going. But the way a liquid base works is you have a table with liquid on it, right? And the same kind of thing, that table is going to drop down after you run a path. So a laser then would shoot the liquid and solidify it. And it only is going to solidify where that laser goes, right? And then you drop the table down and they do it again. And the liquid just stays floating over the top of the model, right? So the table goes down like in a tank. The benefit to liquid based is you can do rubber material. So you can end up with a really rubbery part, a boot, a very soft bushing, whatever you want. All of those rubber type materials, polymers, can be made with liquid based. That's the preferred method for that kind of a material. So it's kind of a dirty process. It's got this chemical, rubbery chemical. There's a cleaning station next to it. You can see it next door that has like rubber gloves and a full, because you have to wash the thing when it's done. Takes a certain amount of time for it to cure. There's not a lot of post-processing. Sometimes it's pretty stuck to the table and you have to just use some sharp device to get it off the table. Solid base is probably what you're used to. That's where you just have an extruder, right? You have some solid wire. A lot of times that's plastic. Could be, a number of different plastic that you can shoot through PLA. But it's basically an extrusion process where you heat it up to the melting point and you lay down toothpaste style material that then hardens very quick. Needs to harden very quick because then it's coming around and making another path. And again, the table's dropping, right? Making a path, table drop, make a path, table drop. So same kind of process. Those are probably the most common. That's what we had first. And those are the least expensive, right? You can get a cheap one for $150, little 3D printer. You can get a pretty good one for about $600. Like they really come down in cost. The tables are pretty small, so the part that you make is pretty small. And then there's powder based, and the powder based are the metal printers, typically the ones that can do any alloy, any powder you put in. Most of them can sinter. So again, it's going to lay a powder base down. A laser is going to track it and sinter it, which means kind of weld the little molecules together. And then the table will drop. An arm will swipe again and lay another layer of powder, and then it'll sinter again. So you'll end up with a metal part that then would need to be heat treated or put in an oven a certain amount of time to make it homogeneous. Means all those little connected molecules that weren't just connected absolutely perfectly with the laser, when it gets heated to the right temperature, then they all just solidify into a nice, clean, homogeneous part that has very few defects, very few, like able to pass FAA inspection for aircraft parts, and that's pretty pure. So they'll take parts randomly off of your run, And they'll cut them and slice them and put them under microscopes to look for carbon pockets or any imperfections. And if there's a certain number of perfection, they'll scrap the part and they'll scrap the process. So they'll say, no, you can't make airplane parts, which is good because we all want to get on an airplane and feel kind of okay about that, right? So it's a really good thing. All right. I have some pictures of that stuff, I think. They're not great, but let's see if we can go slideshows. Slide. I'm just gonna blast through it, looking for, I have some. We'll get back to optimization, because I want to talk about that. I don't know where they are. Maybe I took them out. I think I took them out. All right, so this one, so I went to the National Research Center for Rapid Prototyping. That's in Tennessee. Where they're actually, it's just a facility for experimentation of rapid prototyping. So they had all the different rapid prototyping processes there. This was the welding, automated welding, metal prototyping, where this is literally tracking on a table and then it's going to drop down and track again. Not really much to see, but you can see the part that it's building. Pretty big platform on these, big parts. So then the part that it manufactured was this thing. You can see the weld runs within it. Big metal casting is what it ended up to be. There's a few other parts that they can run. They have a big plastic printer too, giant plastic printer. Then there's some slices, I think, yeah. So here you can see the weldments, right, where it just tracked and laid this thing up. But this is what the FAA would do, is they would slice it and then look at that surface inside and make sure it's just 100% pure. So the things that can happen when you manufacture this kind of thing this way, then you can post-process it and machine flat surfaces if you need to, right? So there is some post-processing on these giant pieces. Here's another one laid up the same way and then post-processing. Here's a chair. It's a big printer that can print that. Yeah.
They're trying to like send, I don't know if it's true, but I read a little bit, but they're trying to send like a, pretty much just a giant printer.
Yeah, so NASA does have a rapid prototyping organization, and they for any kind of deep space, like even Mars, for example, if they wanted to go there, their intention is to be able to build every part of the system that travels there along the way. So yeah, they want to be able to make parts in space as they move. And I think, you know, they really already do it to a small degree, but that's a big part of their deep space program. I wanted to show you some other, so these are all rapid prototyped parts. I think most of these, I think this was the titanium bench. But I mean, clearly, see, these are ports. These are cooling ports that are running along the outside of a pipe. So if you think about trying to manufacture that, cooling port that is curved, that's a very tough subtractive manufacturing thing to do. Pretty impossible. And there's a couple examples of that in here, at least there was. Let's see it. Had a little, oh yeah, right here. This little metal part These are cooling ports that travel around the part and then come out up here. So again, that, you know, the manufacturing process there would be very difficult to figure out. Not sure it could be done. That's a titanium part. Internal structures, there, that's easy. So anything you can model, right? You can 3D print. They have some large printers. So giant, large printers. So these are the ones that they're like producing the chair in and some other things, feet. They're just having fun. This came out of the printer like this.
I don't know.
So you can get all kinds of motion capabilities in your prints. These are titanium parts. Yeah,
How do they print it so it's not attached to the other bits?
leave space between it. Yeah, we can do that. We can print assemblies with our plastic like these. Parts that all move, right? They come out of the printer just like that. If there's overhang, like this has overhangs, I think I printed it in this position, but it still has overhang here. This, when it lays it, it's pretty soft, right? So if there's nothing under it to support it, it'll just fall, it'll droop. So most printers will put in support material for anything that's overhang. Right? The buildup's pretty slow, so if your angle is whatever the printer angle is capable of doing, then it won't do this. But if it's steep and the angle is more than the printer can do, then it'll add some kind of a support material. They're printing with wood, they're printing with, here's the steel, this is a stick off of a backhoe. And when they printed this stick, they went ahead and just incorporated the hydraulic hoses within the stick. So none of you probably run a backhoe, but I have a backhoe and I run it all the time. And it has external hoses that run on the stick. So when I'm brushing with my backhoe, I'm like picking trees up and picking large, you know, bushes out of the ground or whatever, clearing land. Those branches that you're interacting with tend to get up inside of your hydraulic hoses. And if you're not super careful, you go to grab a tree and then, you know, move it off to the side and you have a hose up under a branch of another tree, it just yards your hose right off. Like repairing hydraulic hoses is like an everyday event when you have a backhoe. So this is huge. First of all, we no longer have a hydraulic hose that has to be replaced. The part count has gone way down, right? And now it's internal and protected. It's just a cavity that you would design into the stick, right? So what this is doing is it's making us redesign things and think differently about design. So you all are going to be engineers at some level. When it comes time to design something and you know that you're going to be able to design for rapid prototyping or additive manufacturing, then you can design it however you want. You don't have to think about like, oh, how are they going to build this? Right? Because that's my whole life has been, how are they going to build this? Like, I should be thinking about that. Question.
Yeah, so you're saying you're running like the hydraulic lines through the thing? Or
Yeah. No, there's no hydraulic lines. It's just a port. Yeah, it's just a tube. Yeah, and then they'll process both ends to take fittings, because at some point there's going to be you know, a hydraulic line will go to a port, but it might be like this long, you know, down at the bottom instead of running all the way up to the end. So it's just way more protected. It's gonna have to come out at some point and go into that cylinder, right? Yeah. I don't know where the part. This is good. This is good. I might have not kept the GE jet engine stuff. So another part of this is what's called optimization. So optimization is artificial intelligence within the software. For example, I modeled this very similar to this, right? I just did one piece instead of two pieces. So this was the thing that we had to model. And then we had to just make it one piece instead of this adjustable two-piece thing. Very boxy, very blocky, very designed for subtractive, right? What you can do with the AI software is you can load this. You can put the loads on it that it'll feel in real life. So you have to know those loads. And then run an optimization. And the optimization will then take the load, run it through the part, and understand where the part is loaded, because not all of this is loaded, right? Just a portion of this is loaded. Like these little wings here, probably not loaded at all. It could probably go away. But as engineers, we don't really want to spend the time to like try and figure out what little part of this I need, what little part of this I don't need, right? The software will do that for you, and then it'll come up with the stress paths within the material. So this was modeled, this table was modeled as just a solid from the base up to the top. It was a complete solid. That makes sense? Super easy to model. We model it in about 1 minute. Even my beginning, even you, next term, within 2 weeks could model that. Just a solid circle, loft it between, and it's done, right? So then it sits here, we load it with whatever load is going to be the design load on this table. All right, I got to come up with that. You know, is it going to be 2 people sitting on it and that's the load? Or is it going to be just dinnerware and dinner and that's the load? Whatever. You put it on and then you tell the system to optimize. And there's a bunch of parameters you can choose, like optimize for the least amount of material, optimize for 50% less material, optimize for whatever, right? And it runs it. And then it says, okay, there's where you need the material. And often it's a very organic looking object, very spider webby, very nature-like structure, which again, you're not going to give that to somebody to build. They're going to say, no, we can't build that, right? But we can print it, and we just hit print. Like, I don't know, this was like 78% less material than what we started with, right? So you can take any design, like this has a little more thought into the design. I could load it and optimize it and get some really funky looking thing, right? For example, here's a bike pedal that's been optimized. Bike pedal that's been optimized, right? Print it up. You can actually buy these. It's called topology optimization. So when you get a part and you can take that part as a solid and then turn it into a very organic structure. They're doing this on aircraft all the time now. So there's the starting block, right? And then here's the organic run in the end. I don't think I have. I believe this is the throttle control station on a Boeing aircraft. So where that throttle is for the pilots, that housing looks a lot like this now. And the Portland plant got to do that study and optimization and manufacturing of it. Pretty organic looking. So here's the bracket that they want to design. Here's the mount points. So a lot of times you'll put those mount points in and fix them so they can't move because it's got to bolt up to something, right? So you can't just be totally random with it. But here they're actually changing the position of things and then they're running the software to get a different look at it. But I mean, if you're involved with this, it changes our whole design process. I think. Does this one go through it? Yeah. So here you can see different optimizations of the same design, right? Starting with super blocky and then going down to about as thin as you can get and still support the material. Then you can take and change the entire material to some kind of lattice structure. So you can drop 80% of the weight by going to a lattice structure. I don't know if I have any lattice in there. I think I do. So it's pretty fascinating. That is a pretty small lattice structure compared to a cord. Very fine geometries. It's like pumice, you know, if you've held pumice before, it's super light rock. This is super light parts. All they did was model up the start endpoints, mount points. And then they walked through a optimization. Starts to grow. Then they did a lattice structure. And then they just ran a bunch of optimizations, and then they run finite element analysis on where the high stress levels are and the low stress levels. We can run some of that with SolidWorks too. All right, once you get your part, you save it as an STL, stereolithography. Most printers are going to understand stereolithography. And what it does is it triangulates your part into these triangular shapes. And it understands its thickness and depth and 3D volume in these triangles, right? Even curves, right? Even curves are going to be triangulated. Once that is made, you go to your slicing software, whatever software you use for your printer. This is GrabCAD, which Stratus uses, which is the big printer back there. And you bring your model in. So once the model comes in, I'm just going to leave it in that position, but you can rotate it, make it more efficient, less support material. This is going to require support because we have this overhang here. See how that's overhanging? So there is a better position for this, and that would be to flip it, but I'll run it here just so you can see it. So what it does is it's going to take that solid model and just turn it into slices, right? The better the printer, the smaller the slices, the better the finish, the more expensive the printer, obviously, all those kind of things. But we'll slice it up so you can see it. There it is with its support. So it determines it needs support. A bit hard to see, but you can kind of see it. It's showing me a slice here about halfway up. Fair bit of support to hold it in place. And if you play the animation, it just shows you the slices as you go, both the support and the part. The green's the part, and the brown is the support. So it's just building it slice at a time, exactly how it would build it in the printer. Uh-oh. Go away. Cool. All right. That's it. There's a bunch more slides, but I'm going to put it up on Blackboard if you want to go through it and see all the parts. There's some cool parts, super cool parts. That's a new style of radiator right there. Cooling in, cooling out. Way more surface area than the standard radiators that exist out there. Any last questions?